Hello, everyone, and welcome to EDA Part 2 with Martin Henze. Martin loved the previous session. There was a really good interaction from the audience, and you're supposed to ask questions. You're highly encouraged to ask any kind of question related to data or modeling techniques, or even like the metrics that we are using in this competition, but not just specific to this one. And today is a continuation of the previous talk or the workshop or tutorial, whatever you want to call it, that we had with Martin, and it was really very awesome. So if you have missed that one, just go back after the session today, and you can take a look at that. We will probably also do a short recap of what Martin had covered in the previous session. So Martin, thank you very much for joining us again and for taking the time out of your busy schedule, and looking forward to today's tutorial.
Thank you, Abhishek. Thank you very much for having me again on such a short notice. But I really think we should finish what we started on Wednesday, and dive deeper into the data, dive deeper into the EDA. So what I hope we can do today is to start with a little recap and briefly go over the things that we did on Wednesday for those who missed the first session, and also to catch us up on the little tidying up that I've done on the notebook that's on Kaggle. And then we continue straight where we left off. So I didn't look at the data any further, so it's going to be a very authentic experience again, like it was in the first time. And we're gonna tackle some interesting technical data wrangling tools and tips today, and some more sophisticated visualizations. So that's the plan. Any questions that you have on the first part, that would be a good time to post them now, and we can address them. So you might have seen, so the notebook is on Kaggle, and it's public, and many of you appreciate it, which I really appreciate. Thank you very much. And you might have seen that I tidied it up a little bit. The index always comes with our markdown. I added a little kind of visual, which helps set the mood. So this one is a little bit retro, but it's all about music. And then I added all the narration and all the explanations that we did on the stream, just in the form of talking. And that usually takes more time than the actual code, but it's important because it allows the reader to get into the analysis, and it allows you to write down your thoughts and your interpretations and all of that, so that when you look back at it, even 2 days later, or a couple of months later, you still know what you did. So I added all this narration, like here, the missing values. Yes.
Sorry to interrupt. Would you mind making the text a little bit bigger?
Bigger again. Okay. What about that?
Maybe you can hide the side.
I can. Yeah. Definitely do that.
And zoom in a bit more. Yeah, that's good enough. Yeah, that's perfect.
All right. Yeah. Sorry for that. That's the exact setting that we had last time. Yeah. So you want to say what you're doing, and what you are seeing in these results, and what your interpretations are. I added also a couple of technical notes, so that we use the patchwork package in order to arrange the plots in this way. And I've added the last couple of features that we didn't talk about on Wednesday, that we ran out of time. So speechiness is another one that's very skewed. It's between 1 and it's between 0 and 0.5. Audio valence is one of these features that's between 0 and 1. Time signature is a categorical, or ordinal, and tempo has a different scale. It's kind of around 100 and 200 here. But that followed the same principle that we established in the first session. You want to look at all of your features individually and do some kind of transformations, find the best visualization for them, especially if there are only a handful. And yeah, that's the only thing that I added. We saw that the target is imbalanced. We briefly talked about that. And then we started with feature interactions, and those are just a couple of examples of what we can do. And that's where we will continue today. Excuse me. Yeah, that's where we will continue today. That's where we will put a little bit more effort into finding more comprehensive plots and finding plots that will allow us to explore the data in more depth. All right.
So do you want to start with a couple of questions from the audience?
Yes, please. Do you have any questions on this?
So I don't want to start a war between R and Python here, but there is this question: why did you use R and not Python?
Yes, well, it sounds very familiar. So, like I said in the previous stream, it is largely a personal preference. So, if you feel more comfortable with Python, use Python. For me, I feel more comfortable and the analysis feels more natural in R, because R and the tidyverse methods, they are much closer to the way that I think about data in my head. Right. And to reiterate, you have all these ideas of what you want to do, all this creativity that you have and you're building when it comes to dealing with data. You have to find a way to translate this creativity into code. Right. And for me, that works most efficiently and seamlessly with R. If you want to use Python, if pandas and Seaborn are your thing, then by all means do it. Whatever feels more natural, whatever feels more efficient to you. Having said that, it will be useful for you to speak more than one language, at some point in time, right? So being able to read code in R or read code in languages like, I don't know, Julia, for instance, is going to come in very handy if reading other people's work and trying to understand it. That's also why we're doing this little exercise here of people translating this R analysis into Python. And I've seen some great notebooks on that. So shout out to all the people who have taken upon this challenge. And I've seen some great results. Keep up the great work. But yeah, that's essentially my answer to that.
Yeah, it took. I mean, that's what I always say. Like, use whatever language whatever is easy for you to understand stuff, and it doesn't matter what you use. And it was quite interesting, and I was really happy to see like some people translating your work, what you showed live. And by that time, I think your notebook was not even public, and people had already started, so probably they were just watching the video and translating everything to Python. So I'm pretty sure after today there will be many people who will be translating the work again to Python. So if you're interested in looking at Python code, you can look there, and to get ideas you can look at Martin's videos. And another question that we have, I think this was not answered last time. It's about the question is, while exploring data after seeing the correlation plot, if we want to look for relations between data, would that be mostly between highly correlated data or everything else?
Yeah, so there are two, at least two things here you can do afterwards. So we have the correlation plot right in front of us. So those are the strong anti-correlations in red, the strong correlations in blue. And one of the first things you can do is to, explore those. But you have to keep in mind that correlation always implies some sort of linear relationship, right? Either between the variables directly or between the ranks. So if anything, any kind of more complex relationships are hidden here, they might not necessarily show up in a correlation plot. So if you have some indications from either domain knowledge or some other visuals that you've seen before that kind of motivate you to study the interaction between other variables, then that's a perfectly good thing to do, and that can be a very valuable thing to do.
One more question related to correlation matrix here that we have is, why only take the upper or lower part of the correlation matrix? Doesn't the entire matrix tell us about correlation between the features?
Well, it just repeats, right? So
Yeah, it's just going to be the same. So
yeah, it's going to be the same. If you look at it, so we can do that on the fly here in the code. Right. So is the code size okay? Everything?
yeah, looks okay. If you zoom in a bit more, it would be perfect.
Right, zoomed a bit more. The zoom might not necessarily affect those labels. They
Oh
might,
yeah, sure, yeah.
but I zoomed it a little bit more. So these things should be nicely readable. Okay, so yeah, as you see, it's symmetric around the diagonal, right? So it's like the correlation between loudness and acousticness is the same as the correlation between acousticness and loudness, right? It's symmetric. That's why you can plot all of it, and it might look more aesthetic, but you don't lose any information here if you just take the upper or the lower diagonal.
Okay. Another question that we have is it's quite generic. So can you point to some good resources to learn visualizations using R?
Yes, and but we're going to leave that for the end.
Yeah, that would be nice. Yeah.
Yeah, at the end of the stream, I'm going to give you I'm going to give you a list of resources that you can use to get inspiration and to learn and study this code from from the ground up. We will definitely do that.
Awesome. Sounds good. Then let's take some more questions after some time, and let's continue. Do you want to do a quick recap or move to the next part already?
I think we can move to the next part. I mean, we did the recap. Let's go over it briefly again. We started out with looking at the data, right? Just looking at it in tabular form and learning something about the data types. Found some missing values already. Found some features that might be categorical or Boolean. The size of the data set, right? 15 columns, 40,000 rows. And then we made a kind of a nicely formatted table that we can use to look at the features as well, get an impression. We looked at the missing values briefly, and there's going to be another stream with Rob that goes into much more detail, so I'm not going to say that much about it, but 5% missing values, but not missing values in all of the features. So that's definitely useful to note. I put in some feature transformation already here. So because we found that key and time signature can be best visualized as categoricals, as factors. Whether they should be factors in the model or not, that's a different question. And then both our target and the audio mode feature are Booleans, or logical, as it's called in R. And then we built this overview kind of dashboard-like plot. So all the different features and their distributions in one overview plot. And that's something that can be very useful for communication. The dog agrees, if you can hear him. And that's something that you can open any presentation on your data analysis with. Or if somebody in your team asks you, hey, this new data set that you're working on, what's it like? You can give them one plot, one slide, and show, yeah, there are these features. Instrumentalness is weird. Key takes discrete values. Audio mode is a Boolean, and so on. So there's an advantage of having them all in one place. Also, in your analysis now going forward, you can always go back to this plot if you're looking for ideas, and if you want to check something, you can see, okay, danceability had this distribution. That's something I need to consider when going forward. We saw that the target is imbalanced, about 60-40. And we found, and this is something that we're going to dive deeper into. We looked at a little bit of the target impact. We had this nice correlation matrix, and then everything else we're going to redo anyway. Sounds good?
Sounds good. Seems like someone agrees.
Yeah. The dog has very strong opinions about data visualization. That just comes from working with me. All right.
Let's carry on.
Let's carry on. We're gonna do. All right. We're gonna continue with feature interactions, because, like I said, we now know what all these distributions look like. So we can now look at them in the light of how they are affected by the target, and in the light of how they interact with each other. So we have this distribution here for song duration, right? And we can color it by the target, and we saw that, well, the two distributions are almost the same. And we can do the same thing that we did at the beginning and look at all the distributions and features individually in the same way, but we're going to be a little bit more clever and a little bit more technical about it. And I have to remove this. And this is one of the main technical things that I want to talk to you about today. And we're going to do it right at the beginning so that we're still fresh. So if we look at our training data, right, it looks like this. There is a row for every observation, and there's a column for each feature. And, that's the ideal case. And that's the case that you often find on Kaggle. And that's what's called, many people call it tidy data, right? Especially in R, but in general as well, right? One observation per row, one feature per column. And if you're working with data, in the real world, you'll know that, tidy data like this is not something that can be taken for granted, right? Real world data can be very messy, and very often the first part of your analysis is to get it into a shape like this. Now, for looking at it and for kind of understanding it as a human and for showing it, this is the best format. But in order to build some of the visuals that we want to build, we want to wrangle this data further and transform it, right? So we're going to work with something that's not going to be this table, but the table reshaped. And I'm going to show you how to do that. So we're going to build plots that show us the impact of the target on the different distributions. And for that, we want to start with the numeric variables only, right? Oh, this needs I think a cross is using that now. Okay, vars maybe. See, this is live. This is live and a barking dog in the background. What am I doing wrong? I want to... All right, well, let's look it up. This is live. Oh no, not select, but across. So across is a new function that was recently introduced to make it easier to do operations around kind of along multiple columns. And I think it's what we need here. So cross starts with round. I mean, but that's the way it goes, right? You can't know everything, but you want to know where to look for it. All right, let's do it differently for now. I'm a little bit rattled by the dog, I have to admit it. Let's take out the ones that we know are not what we want to have. So audio mode. If there are any R people in the audience, I do apologize for that. If you want to put the solution in the comments, feel free. Time signature and minus. Oh no, we need some popularity. All right. So now we have only the numerical features, and maybe also don't want key. and our target. And now we can do a thing that's called pivoting. So we're going to transform the data from this white shape into a long shape. And this is going to be everything except for some popularity. Let's see if this works. Names to, we'll call it type, and values to call it value. Right? And there you have it. So this is now the whole table, kind of the white table that we started out with, squeezed into a long form. So we started out with these 10 or so numeric columns, and now all of them are here in this type feature, and their values are in value, right? Now, why would we do that? That's much harder to read, but it's much easier to visualize. All right, so now we can do something like this.
It seems like you deselected audio mode twice. There's a comment about that. Does it matter?
No.
Okay.
But good catch. All right, so we can do that, and then geom density, right? And that's not very useful because that's, we also want to, let's drop all the NAs for now. Okay, this is not very useful. This is the, what was it called? Instrumentalness annoying us again. But they're all now in one plot, which is not what we want. And the reason we did that is because we can now use something called facets. We could facet wrap around the new variable that we made called type. And then it looks like this, right? All the features now get one facet. But at the moment, they also share a scale, which is not very useful. So I'm going to say scales is completely free. Yeah, completely free. All right, and now we're getting somewhere. So this is a way we could have started out at the beginning instead of doing this individually. We could have done this and turned it into a long format and then plotted all the facets next to each other. But we did this here purposefully, so that we could look at each feature one after the other and think about its distributions and its characteristics. And now, this is the reason why we kept the song popularity. We can fill it by song popularity. Okay, and don't forget to add the transparency. Right, and there you go. This is what we, where's the song duration? Here's the song duration, right? This is what we had earlier. Now we have them all in one place. We can look at the energy, we look at danceability, audio valence. We can look at all these things. We want to do something about instrumentalness, and we can definitely do that. Before we pivoted, we would just transform it. So it's called instrumentalness is 10. Instrumentalness. I think there were some issues with that needs to be larger than 0. Right, so we're back at this kind of visualization, and if we have some time, we're gonna look a little bit closer into this feature afterwards. But for now, that should do. We have the shared legend here, song popularity. We can put that at the top. Do a little bit of prettifying it. Position goes at the top. And we go for the title. target impact, numerical features. And there we go. This is our plot, right? So we started out with this, or something like this, and then we replicated it for all the numerical features through the technique of reshaping the data from a wide format into a long format. So now that we can use this facet wrapping here on this new variable with all the feature values in here, and we can identify the feature itself through here, which gives us this. Right, so asking for any questions on this, and just to kind of reiterate, this is one of the main techniques that you can use in order to unlock additional visualization methods and visualization styles for your data. You need to reshape it a little bit so that you can kind of reassign styles like color or facet, or the size of points, or the filling of a certain curve to these new variables, and then you can find new ways to display them.
So right now we don't have any questions about this, but there is a question about transformation, if you would like to answer that one.
Yeah, let's give it a go.
So the question is, can you talk a little bit about when to use what type of transformation, and do we need to apply different transformation when data is left skewed or right skewed?
Yeah, I mean, the main purpose of these transformations would be to get your data as close as possible to a normal distribution, right? When it comes to, I mean, if it's continuous, when it comes to dealing with distributions, we always want those to be normal, because they're super well behaved. They don't have any kind of strange multi peaks, and we know how to deal with them in a very kind of rigorous statistical way. So what happens quite often, that you can you can see a distribution like this, or you can see this instrumentalness that we had that was extremely skewed, and you start with a log transform, because a log transform is kind of stretches out the earlier parts and then condenses the later parts. And that should get you already much closer to understanding what's going on. Because if you only see the original instrumentalness, that doesn't tell you anything, right? It's all the kind of variance is hidden here in this one bin, and it's not very useful to understand what's going on. This might be different for a model. Maybe you find a way to to feed this into a model, but even a model needs to have some idea about how to distinguish certain things. So that's why we transform it. And those are transformations here specifically that are primarily geared for making it easier to visualize and to get kind of visual insights. But they can already tell you something about what kind of pre-processing you want to do for your model, because maybe your model will have difficulties with an extreme skew like this. And scaling won't fix it, because scaling just leaves the proportions intact and puts it into a different range. So you want to consider making it easier for your model to deal with these data by transforming them in a certain way, and by visualizing it, you get an idea what kind of transformations you can use, right? So whenever there is a kind of a right skew like this, although this is not extreme, and those are kind of different because they are more closely related to probabilities between 0 and 1. But whenever there is a very strong right skew, you want to start with a log and then take it from there.
Okay, and we do have two questions about correlated data and features. So one of them is how correlated data will be helpful in tree-based classification. Does it impact if the result does it impact the result if the data is correlated in a tree-based algorithm? And another question that we have is, if two features are highly correlated, shall we just pick one? Let the model decide, like the previous one, or what should we do?
I mean, for most of the more sophisticated models, it really doesn't matter that much whether there is, collinearity in there, because in many cases the model will deal with it. It becomes important though if you are, interested not only in the predictions themselves and the output of the metric that you get from your model results, but if you're also interested in the interpretability of the model, right? When it comes to having an interpretable and robust model, then the fewer features as possible is the best way to go, right? So if you think that by eliminating one feature, you can keep the performance of the model practically the same, but you have one fewer dependency, then that's a good thing when it comes to robustness and when it comes to understanding what's going on in the model. So that's my view, at least. What do you think, Abhishek?
Yeah, I leave most of the stuff to the model for it to decide what to pick and what to throw away. So now we have a few questions about what you showed just now, and what is this technique called again? Like, what are we doing here?
So there are two techniques at play here, right? One is this facet wrapping. And I know for a fact that Seaborn has something like facets as well. Right? Facet essentially means you pick one feature, a categorical feature, or kind of ordinal with a kind of small number of distinct realizations, and you use that to split the data into different subplots or facets. Right? That only works up to a certain number of, if there would be like 100 types or so, then it's probably not going to look good. And that's a way of kind of assigning another visualization style and visualization kind of variable to one of the features, right? So you have things like, when it comes to a visualization, you can assign features to X and Y, of course. You can have color, you can have like a line type, a size of a point, or something like this. So you are able to put quite a few different features into the same plot, but the more kind of these details you add to a plot, the more difficult it becomes to understand it. And the facets, they are useful in the sense that they don't add a lot of noise to, well, they don't add any noise to the individual plots by themselves. They add a little bit more kind of cognitive complexity to the whole thing, because you should consider the whole display as one plot. But they do it in a very clean way, in that all the different categories here are put next to each other, and you can look from one to the other. You can kind of look from energy to danceability and see that, okay, for energy there is some difference here, right, and some popularity for the high energy levels and the mid energy levels, whereas danceability there's a tiny difference, but it probably not going to account to very much. So you can kind of you can look from one to the other, and you can study them one by one, or depending on what your facet plot shows, right? It could show something like the evolution of a certain distribution over the 12 months of the year, right? For instance, January, February, March, April, and you kind of have them all next to each other, almost like a calendar view. And it's a very clean way of kind of getting another visualization dimension into your data. Oh, so this is the one. This is the facet wrap, and then the other technique that we're doing here is the reshaping through the pivot. right? So we're turning, let me show it again, next to each other. We're turning this wide format into this long format. And we're doing this explicitly because we are aiming to use this new type feature here as a visualization dimension, right? And we're doing it through Facet, but you could do it through other things as well. So let's do that on the fly just to show you what I mean. We can take all this and say we don't care about popularity, but we care about type. Then we leave that the same. We don't want facets, but we use type now as the fill color, right? And well, now they all share the same axis, so it doesn't really work. So maybe let's take out instrumentalness. It's going to get us a little bit closer to. Of course, if it's taken out, we can't modify it. Okay, which ones? Oh, song duration. Now you see where this is going. Song duration. Typing is hard. All right, let's do it the other way around. Where you select, let's say, danceability and acousticness. It has to be enough. Which is okay. If this doesn't autocomplete, then something doesn't work. All right, so let's do it. And acousticness. Oh, we don't care about. So, all right, let's leave it in there just for simplicity, but we're not gonna use it. Okay, so the same thing. We're gonna just take these two, turn them into. Okay, we're just gonna take these two, turn them into a wide format, a long format, excuse me, right, where we have to type here. And then we use the type instead of the facets above, we use the type as a color, right? We can add another one, audio valence. And we'll get another color. Right, and we can show the overlaps like this. So this is the main advantage, the main purpose of this technique, to reshape the data and not really transform, but reshape the data in a way that that allows us to use new visualization techniques that we couldn't really use before.
So yeah, that's great. And yeah, okay, there is one more question. I don't know how much we should answer this one, but you have already answered the first part of this question. So the question is, can you comment a bit on what the graphs tell you, which you have already explained a bit? And the other part is, so it comes across that as there's no real distinction between popular and not popular. So what's your opinion, Martin?
Yeah, it sure looks like that, right? So here the idea is to see whether the distribution of these features is notably different depending on the target. So something that you would hope for finding is that acousticness, the blue peak is here, and the red peak is here, right? That would indicate that this is a very strong feature when it comes to predicting song popularity. But none of these features really are very strong on their own, right? This is what we're looking at, the features on their own. And that goes a certain way to understand why the leaderboard scores are the way that they are right now, right? Last time I checked, it was somewhere around 0.6, maybe a little bit higher AUC, which means that this is really not easy finding a strong prediction here, finding a strong model here. And that is reflected in the data. So if you find an interesting feature here, you can follow up further in additional analysis, and that's the purpose, right? It's not so much about the shapes of the distributions, because the shapes of the distributions we looked at here already, but now knowing those general shapes and having done that, we can look at we can separate them by the two target values and see whether there are any differences. So maybe this could be interesting. Energy, there's some difference here. Audio valence has some difference here, and they both tend to be lower for popular songs, right? There's a little bit of a difference here in tempo as well, but tempo and energy, there might be some relation there. So those are two, whenever you see a difference, and here we don't have any strong differences, so we have to look at the smaller differences, as opposed to something like this, which is almost completely overlapping.
Okay. Yeah, I know it's a difficult problem. And
well, you should know.
Yeah, but I don't want to. I don't want to comment on the data or anything. Yeah, people need to try some stuff, and some things will work. So this discussion that we have is also connected to the previous one. So takeaway after looking at these plots, you have explained this a few times now. So now, what do you think, like when we are looking at these plots, can we figure out what's going to help with modeling?
Yeah, like I said, I mean, there's no kind of strong smoking gun here, and it's more about finding some hints of what we want to study further, rather than an immediate indication of what could be useful for our model. And keep in mind, we're doing kind of EDA only here, where we haven't included any models yet in this work, and in many cases, what you will find is that there, is a useful overlap between EDA and modeling, right? You can use your model as a sort of exploration as well, see what kind of feature importances you get from your model, and then study these features further. But before you do that, you want at least a basic understanding of what your features look like and how they're distributed.
Sure. Let's take more questions after some time, and let's carry on with the analysis.
Yes. Okay, so we have to modify things a little bit for the categorical variables. I mean, audio, we said, should be a binary. Well, we kind of transformed back to a factor here between 1 and 0. Then let's see how we do that. Let's take it step by step. So we did the numerical ones all in one plot. Now we want to look at things like, let's say, time signature, also popularity. and then geom var. Okay, and we can put them next to each other with position dodge. Okay, and that is potentially more interesting than what we've seen before. Right. So for like we did in the initial exploration for continuous features, you want to start out with a density plot or a histogram. That's the ones that I prefer. At least start out with them. You can always use a box plot or something else, or a violin plot instead if you find it's more useful. But starting out like this, it usually gives you the most efficient workflow. And then for the categorical ones, you want to use a bar plot. Right, and again, you can use different ones if you find different ones are more useful. Okay, so here, this is interesting. Time signature. There's quite a difference between the unpopular songs and the popular songs when it comes to time signature. And in a similar way as we faceted the continuous features, we can do the same for the categorical features. Right? We can think about, let's see, turn this into 2 rows. Right, it's a little bit prettier. Oh yeah, and we forgot dodge. Position dodge. All right. And that's nice. Although, oh, okay, yeah, they are, of course, those are absolute values. They are not normalized. That would have been too nice. Okay, so I take back what I said before, at least parts of it. Because it's imbalanced, we have this imbalance still in here. And this imbalance looks similar, most of them. Now there's going to be a way we can deal with that on the fly. What we need to do is to group things, and then we could use gmcall. Let's do that quickly. Let's try to do that quickly to get an idea of what we would do. I'm going to start with a pivoted one. Okay, and now we want to group by type, and then song popularity. So group is the same as in pandas, and then you can summarize, which is called aggregate in pandas. We'll just count. Okay. So audio mode false is that and that many. Audio mode true is that and that many. Oh no, that doesn't help. We need to group by value, of course. Right. So now we have all of those values. Now this is grouped by value. And we have type, song popularity. Summarizing removes one level of the grouping, which you see here. The remaining groups are type and song popularity. So you can now, within those groups, get this. Let me think for a moment. That's the wrong way around. You want to have value and song popularity. It's all live, people. It's all live. Okay, so type and value, because now you want to frag is n over sum n. Okay, what did we just do? We had, those were the two groups that were left. Right? Audio mode has either value of 0 or 1. And it can be, some popularity can be either false or true. And because it's imbalanced, there are more false than trues. And this is the overall fraction that we get out. Right? So we can compare the fraction of falses for value 0, 6.3, 0.63, and it's very similar for false. Okay. Now, this is interesting. I didn't expect to do this, so bear with me for a moment. We're first going to remove all the groups. This is just so that the data itself is clean. Then there is some redundancy here between true and false, right? Because one is one minus the other. So we're just going to remove all the song popularity equal false. Yeah, you know what I mean. Okay, and now we have the fraction of the true for the different values that the different types take. So now let's plot something. Let's do this. We want to plot value against fraction. And we want to fill it by type. This is now going to be, so there's a difference between geom_col and geom_bar, which is that one does the counting by itself, whereas the other one, you kind of supply it with two values, two variables. And then all of this blind, so it's either going to work or it's not going to work. We will facet wrap it also by type. Then we're going to be super optimistic that this is going to work and set the themes that we want, because we want to do that anyway. Might as well do it now. Top. And then labs, title, feature impact, categorical features, target impact, of course. Whew. Okay. So let's make it a little bit prettier. Scales. We're only going to free X so that we can compare the Y values. All right, so you might have been able to follow or not. I don't blame you if you didn't. I barely managed to follow. Now, so, what we did, just to quickly summarize what we did, we kind of went into this and normalized it by the overall numbers. So this is now the fraction or the percentage of trues, so the popular songs, for the different features, the different categorical features that we looked at, over their feature values that they take. Yes. Abhishek, you were going to say something?
Yeah, I was just saying that the legend is it's a little bit small to read on screen. at least for me. So can you say like which one is which?
Oh yeah. So hang on. Wrong axis. So this is audio mode. There's a way. CX. There's a way to make these larger. I'm gonna make these larger in the final thing. So this is audio mode, this is key, and this is time signature. Right. So for audio mode, it's almost the same. For key, there's a little bit of a difference. So we're between 30 and 40% here. And for time signature, there's a little bit of a difference as well. So this is the percentage of popular songs per feature, per feature value.
Okay, so just the popular ones.
Just the popular ones, because you can plot the popular and the unpopular next to each other, but one of them is one minus the other. So you get all the information from one of them. That's why we did it this way here.
Okay, sounds good. I don't see any questions on this part from the audience yet, probably because of the YouTube lag.
That's
But there,
we're gonna do one other small thing that I promised last stream that we would do. We're gonna use this pivoting trick to do our own quick missing values visual, right? So I'm gonna leave. Let's put it here. Let's put it here in between the interpretation. And you might see where this goes. So here now we just pivot everything. You can call it literally everything in R. That's a nice thing. Names to, so the column names go to, let's go to feature, and the values to value. Oh yeah, we need to cast everything to rotate. Oh, I really hope that works now. Across everything as numeric. Huh. See, sometimes things work. If you want to take away something from the stream, sometimes things work. Now we have all of them in here, and we're gonna get the fraction of NAs. So for that, we're gonna need to know whether these values are NA or not. So make a new column called is NA. Which is just this, right? And we want the fraction of NAs. So true is what we're interested in versus false. And you can do the same thing in Python and pandas. That's a convenience thing. You can take the mean of a Boolean variable, and we'll treat false as 0, and then we'll treat true as 1. So call this NA frag, and that's going to be the mean of is NA. Oh, and we need to group by type, because so we already know overall it's this 5.3% here. It's nothing new. Oh, we called it feature. See, that's what happens if you're inconsistent. Okay, and now we can plot this. So we're going to make this quick. This is feature against NA frag, and we are going to say, I'm going to fill it with feature and gem call. Okay, so we have these fractions of the NAs, the percentage of missing values. Gonna do 2 things before we're gonna do the next thing. Choose our favorite theme. We don't need the legend again because we kind of overloaded the visual features here. Right, and then one thing we're going to do, we can reorder by one of those to make it look nicer. Like this, right? So now they're in order. And then because we want to be able to read, the features, which, ironically, you might not be able to because the font is so small for some reason, we can do a thing that's called Chord Flip, which does exactly what you think it would do. Right, it turns the x-axis into a y-axis. Okay, so now we remove those and call this percentage of missing values by feature. And we promised a percentage, so we should deliver a percentage. There we go. Right, this is our very own plot. It doesn't have all the information in here, so you don't see how they are distributed within the rows, but you have a quick overview over it to very quickly kind of regroup and count alongside what would otherwise be a column-wise view.
Yeah, I find it very interesting. I'm not sure about others. But like only a few features have missing values, and the percentage of missing value is almost similar in all of them.
Yeah, it's around 10% for about half of them, right?
Yeah.
Which gives us this percentage of about 5% overall.
How easy would it be to get the same plot for test data?
Oh, extremely.
Just have to change train to test, right?
Yeah. And like we talked about previously, you don't really want to look at the test data, but for missing features, it's fine. And you see it's a similar thing. A little bit less than 10%, a little bit more, but this could be a size effect between train and the test.
I would think like there is something here if the percentage of missing values is similar in train and test. So sometimes it's good to also take a look at test data, right?
Yeah, sometimes it's good. And I mean, something that you can do is always a quick adversarial test, right? You can try to train a model and use train and test as the labels and see whether your model can distinguish between the train and the test set, without you having to look into the test set yourself. And that way you can try to figure out whether there could be systematic differences.
So assign all labels for train as 1 and all labels for test as 0, and then train a model.
Yeah.
How would you interpret that? Like, what kind of metric should you use, and how would you interpret that? Like, if it's AUC of 0.5, then it's they're very different from each other or similar?
Well, if it's AUC of 0.5, as you know, all the people have found out who tried to climb up the leaderboard, then it means that there is no predictive power there. So if it's AOC of 0.5, then the train and the test set are very similar in terms of feature distribution, and the person who prepared the data has done a really good job.
Yeah, okay. Yeah, let's see. I've not done adversarial validation on this data yet. I hope someone does it. So we do have, since we were talking about NaN values, we do have a question here. And the question is, as of now, we have been dropping all the rows which have NA values. And what if we impute those NA values with some value and plot the graphs again? They might not be the same again, right? And could you talk a little bit about this? So since we are also talking about NaN values, I would like to mention that we are going to have a session with another Kaggle Grandmaster, Rob, on Monday, and we are going to talk about handling missing values in tabular data exclusively. But yeah, I would definitely love to get your thoughts here, Martin.
Yeah. So when you do imputation, you have to decide how you do the imputation, right? So one very simple way would be to use the mean or the median, and in that case, your distributions will change because you add more values in the mean or the median. So here the median would probably be somewhere around here, and you would kind of just make this peak higher. You can, by definition, you cannot learn anything new about your data because you are inferring the missing values based on what you already know about your data. But yeah, technically the distributions would change, and you might want to look at this change that you are enacting through a certain imputation strategy to see whether it makes sense, or to see what the outcome would be. That's something that you could easily visualize. Okay, so I'm happy that we covered the pivoting, we covered the reshaping, we covered the facets. That definitely is something I wanted to do. We learned something about the target impact for the categoricals and the numerical features. And now I want to take us a little bit deeper into the correlations in the time that we've left. So we started with this correlation matrix, and you can always let's see what it's called. Method, right? You can have the actual numbers themselves. Oh, they might be too small for you to see, but this is 0.64. Those are both kind of between minus 0.5 and 0.6. So let's change that back. Oh, let's make it a square. I like squares. The dog likes squares too. And like we did before, we have these kind of strong correlations between energy and loudness, and we have some correlations between the categorical features as well, like time signature and audio valence. So let's find a way to explore those further. So this is what we did here. We did feature target interactions already, and we can always throw in the target as a color. But let's build on something like this. Let's build on something like this. One thing you can always do very easily here is to just put a smoother into it to see what it looks like. Oof. Or maybe not that easily. It's doing something strange.
In the meantime, shall we take a question?
Yeah, we can always throw in some questions.
So the question is, what kind of relations shall we look for between the three categorical columns and every other column?
Between the, sorry, say that again. My session just crashed. I have to rerun stuff.
Yeah,
Can you say
sure.
that again, please?
Yeah. So what kind of relations shall we look for between the three categorical columns, key, audio mode, and time signature with every other column?
Yes, exactly. So this is precisely what I wanted to talk about right now. So when it comes to, there are different visualization techniques that can use for categoricals versus numerical ones. So let's take something like danceability or energy. Energy looked like it might be interesting, right? So let's take energy and look at the interactions that we have with time signature. Energy. No, that's not what we want. One thing after the other. We're going to use the density plot, which means we want to fill it by time signature. Yeah, some missing values here. Just forgot it. The dog is protecting me from something. It's probably, bad visualization choices, but I'll make those anyway. So, unfortunately, his mission is doomed to fail. Okay, so this is one way, right? So there's a definite interaction here between time signature and energy. The lower time signatures, so this is 2, 3, 4, 5. They have higher energy. No, lower energy. Lower time signatures have lower energy, especially when it comes to 2 versus 4. 2 versus 4 is a big difference here. Let's see how we do. Okay, so this is one way to visualize categoricals versus numerical features. And you can take this further. So you don't have to restrict yourself to 2 dimensions. So let's take this further. Let's say we want to look at energy and was one of the other time signatures, one of the categoricals, and key. Okay, so it's a key and time signature. Now we want to fill it by energy. And instead of geom density, we want to use geom tile, which gives us a heat map. A heat map that looks like this. So depending on how your resolution is and how good your data is, this will look more or less interesting. So kind of fill. I'm going to use Viridis. Okay, so now a brighter scheme means a high energy, and a brighter color means high energy, darker color means lower energy. Right, so you have this relationship between key here and time signature, and what we're doing, we're taking this kind of 2-day plot into the third dimension. So time signature of 2 has lower energy, which is this, and time signature of 4 has higher energy, which is this. And this higher energy seems to be happening kind of largely all over the board. but possibly primarily for higher keys here. Right, so this way you have the possibility to get another dimension in, and now this belongs into feature target. You can do our favorite faceting trick and wrap that by target, not target. The target in this case is called song popularity. Okay, the popular songs on the right, the unpopular, well, let's make it top and bottom. So the popular songs on the bottom, the unpopular songs on the top. And so the thing that you're looking for here is clusters. There's no real clusters that I would identify. There's some differences here. This is a difference that's notable. So the combination of key 6 and time signature 4 has much higher energy for the popular songs than for the unpopular songs, right? So this is a way in which you can look for how you can find interesting differences in your target variable, not just for individual features, but for the interaction between individual features. And this is for categoricals, right? This is for categorical versus categorical versus numerical, really, because that's what we kind of started out with. And then you can do something very similar, like what we did here. I'm gonna blast through this a little bit, but we're gonna take questions afterwards. Let's see what we found. What are the most interesting numerical features? So we have energy, we said, and possibly audio valence. There's some difference. Tempo. Let's use audio valence. Okay, so again, a very shortcut. You can make this cleaner by just removing the missing values that you're not interested in. Energy, audio valence. So we had these Gian points, give us something like this, but we can also, similar to the 1D density plot, we can use a 2D density plot, like this, or filled, right? So now energy is peaking somewhere. Energy is peaking here, and audio valence, it's a little bit flatter, but it's peaking here somewhere. So we have these 2D relationships now, and we can do the exact same thing. We can wrap it by song popularity. Okay, and in this case, the differences are minimal. Again, what you would be looking for here, ideally, is that some of those peaks would shift between true and false, but they don't really. Which is a shame, which kind of tells you that this interaction between those features might not amount to much in compared to the features individually. All right, so in that way you can go from having your correlations and having your individual distributions to kind of two-dimensional comparisons between features, kind of 3-dimensional comparisons. Then you can bring on the target feature as well, compare back and forth, and kind of use different styles of visualization for categorical and for numerical features. All right, that's going to be as far as we take it today, I think, and we should definitely take some time for questions.
Awesome. So we have we don't have much time. We have 9 minutes left. Let's see how many questions we can take. So if so, this is an interesting one. So if it was not a Kaggle competition, after doing the EDA and getting such overlapping values, would you go for a machine learning model or not?
Yeah, absolutely. I mean, you can always try out a machine learning model. There might be some more differences here lurking in some of those feature interactions that we haven't found yet, and a model can help you to figure out which those might be. And you can always run a model, see what the result is, and then kind of iterate. So this is always an iterative process, right? You do a little bit of EDA, you do some modeling, then you might have to go back to EDA to understand better why those features have an impact, and you do more modeling. So it's very iterative.
So another question that we have is, when you say not to look at test data, do you mean to ignore the distribution of data in the test set?
Yes. I mean, you can use this adversarial method that we talked about earlier to figure out whether there might be a difference between the two. But remember that the test data, the purpose of the test data is to serve as an independent validation of your model. So for the test data, you are predicting on new data that the model hasn't seen yet. And in order to properly validate the performance of your model, you don't want to be influenced by the test data. And that doesn't just include that the model shouldn't see the test data, but ideally you shouldn't see the test data either, because you are part of the modeling process, through selecting a model or making certain hyperparameter choices. So it's always best to leave the test data alone as much as possible. At least that's my perspective.
So in the talk today, you showed a lot of data reshaping techniques. So the question is, how feasible is the data reshape technique with huge data sets?
Well, with huge data sets, in general, what you want to do is to start with a subset. Ideally, it should be a representative subset. But when it comes to EDA, you like you saw, we are often building plots and then we're discarding them because they're not useful. So this might not be included in the final notebook because there's not much difference here. You want to move quick, you want to iterate quick, right? Same as with your initial modeling stages. So you want to work with a subset that's kind of small enough so that you can handle it, but still large enough to give you some useful insights into the data, so that you can again iterate quickly and move quickly from visual to visual.
Okay, the next question that we have is about columns filled with negative values. So how do you approach column filled with negative values? Do we eliminate the column or try to convert it to a categorical column? So I don't know why we would convert to categorical.
I don't know either. I mean, negative is fine, right? There's
It
no,
is.
yeah, it would be a continuous variable that goes from, I don't know, -50 to +50. That's fine. It doesn't matter whether, it doesn't have to be positive.
So treat it the same way as
Yeah.
other features. Yeah. Okay.
Yeah, I mean, there's certain transformations that you can't do. You can't do a log scale on negative values, obviously. But other than that, there's no real difference.
Okay. Another question that we have is: are extensive EDA and feature transformations worth putting a lot of effort if we know anyway we are going to use tree-based models?
Yes, because remember that. I mean, it might sometimes be a little bit different on Kaggle because you can get away with only caring about the leaderboard. But in general, when you're building a model, you want to not just to understand and be able to interpret the model and the selection that it makes. You also want to be able to communicate your modeling process to the people you're working with, right? To the people from which you get your data, to the people to which you kind of deliver your models or your insights or your dashboards. You want to be able to say, this is what our data looks like. This is what we're doing with it, and that's what's getting out of it. It all in the real world. This process doesn't exist in a vacuum, but communication is very important, and a great way of communicating is through visualizations.
Yeah, definitely. And yeah, when you're working with people, you have to show what you have found in the data before applying the models.
Yeah.
So this question is, once after pre-processing your data, is it wise to look for data trends again, or is it prior to any kind of pre-processing that we try to understand our data?
Yeah, this is again, that's an iterative process, right? So like we learned with this instrumentalness column, which for which we didn't have time to look into it in more detail, that we need a transformation here. And then after that transformation, you can go back and understand a little bit more about it with other tools, right? So this is not a strictly linear thing, right? Again, it's an iterative cycle. You do a little bit of EDA, a little bit of modeling. You find that you need to understand something better, or you find that you do understand something better, and then go back and do a little bit more EDA, and then a little bit more modeling again. So whenever you find something new that kind of changes your insights about the data, it's perfectly fine. It's very common to redo some of this analysis and get step by step a little bit closer to the truth.
Okay, that's great. And we don't have much time left, but I would love it if you can answer this question about when we are doing EDA, what should we look for? And when we are starting with EDA, so like people asked in the beginning, what kind of resources would you recommend? Where should we start from if we want to perform EDA on any kind of given data?
Yes.
What do you
So
recommend?
yeah, so let me try to summarize that. The kind of the process that I'm following is what we've been talking about in these last two sessions. You start with looking at the data, then start with the individual features, look at the impact of the target, and then kind of get more and more complex until you're kind of looking at multi-dimensional plots and resources. That's definitely something I wanted to bring up. So there is this great book called R for Data Science. It's completely free, written by Hadley Wickham, which is kind of the mastermind between the R tidyverse, all these packages that I've been using today and on Wednesday. And this is how I started with using the R tidyverse for EDA. It's a wonderful book, and you will learn a lot about data transformations, exploratory data analysis, and you don't even have to use R. You can just follow these ideas that are outlined here, and it's fantastic. And when it comes to visualizations, a big recommendation that I have is to follow me on Twitter. No, you don't have to follow me on Twitter, but you're welcome if you want to. But there is this Tidy Tuesday hashtag on Twitter. And that's the thing that happens in the R community. Every Tuesday, there's a new small data set, and it's a data visualization challenge. And people come up with all sorts of amazing plots, right? Look at this. This is just, I mean, it regularly blows my mind what people kind of build in these challenges here, right? And they always publish the code. They publish the visuals. They publish the code. It's always great. It's a great source of, with maps, it's a great source of inspiration and sample code that you can just copy paste and adjust to your own project. So this is where you get your basics, is my recommendation, and this is where you can just get so much inspiration and ideas for how to use data visualization to effectively gather insights and communicate your findings.
Can I recommend one more resource?
Absolutely.
So Martin has a series called Hidden Gems.
Oh, yeah.
And you should definitely follow that series. He's releasing the hidden gems of from Kaggle, the notebooks, and these notebooks have a lot of information, really different kinds of visualizations and EDAs in each and every one of them. And now it's volume number 89, I see.
Yep.
And each volume has 10 hidden gems.
Oh no, three.
Three. So like almost more than 250 hidden gems.
Yeah, we're getting closer to episode 100 to 300 hidden gems. It's very exciting.
Wow. So like 300 different notebooks you can learn from. I mean, that's amazing resource. And he's putting a lot of time going through all notebooks and choosing the best ones. So yeah, we are out of time now. I know you're on tight schedule. So thank you very much, Martin, once again, taking your time out. And thanks a lot. It was a lot of good learning experience, even for me and for everyone else who has joined. Thanks a lot for joining me.
Thank you so much for having me. It was great fun, and thanks to everybody for for your enthusiasm for participating in this challenge. And it's going to be a very exciting thing going forward. Thank you.
And follow Martin on Twitter and the Hidden Gems series. You will learn a lot from it. And have a nice weekend, everyone. Bye.
Bye-bye.